Hello everybody, getting ready to do lesson 7.5 part 4 of pre-calculus math today. And for today's lesson, we got 12 points here will go into our notebook. And we got 32 points that will go into your class worksheet. Students, have that out in front of you. Have your notebook guide ready to go or your notebook out. And for today's bell work, students, teachers, here is our today's bell work. Let matrices A, B, C, and D be of the dimensions 2 by 3, 2 by 3, 3 by 2, and a 2 by 2, respectively. Determine whether the matrices are a proper dimension to perform the operations. If so, give the dimension of the answer. So for 95, we have A plus 2C, and give us the dimension of that. And B minus 3C down here for 96. Give us the dimension of that operation. Teachers, give your students about 5 minutes for these. Pause your video and I'll be back in 5 minutes. Okay everybody, for today's bell work, our solutions for today's bell work. A plus 2C will be a 2 by 3 plus a 2 times a 3 by 2 here. So when we add that together, it is not possible. A and C are not of the same dimension. We have a 2 by 3, 2 rows, 3 columns. And then our C here would be 3 rows and 2 columns. So you can't really combine those two. And then down here for a B minus a 3C, a B here would be a 2 by 3, 2 rows, 3 columns. And then our 3 times C here would be 3 rows and 2 columns. So we have 2 rows and 3 columns, and then 3 rows and 2 columns. You will not be able to combine that either, so it's not possible. B and C are not of the same dimension. Okay, for today's lesson, properties of matrix multiplication. Let A, B, and C be matrices, and let C, small c here, be a scalar. So number one property be A times BC. Matrices will be equal to AB times C, associative property of matrix multiplication. And then 2, A times quantity B plus C will equal AB plus AC. It'll be left distributive here. So this will be left distributive. Your multipliers on the left-hand side. And then A plus B times C here, quantity A plus B times C, will be right distributive, AC plus BC. So AB plus AC here. So you have a difference here of order. Will change your quantities and your matrices. We know that matrix multiplication is not commutative, so remember that. And then here, our scalar C times AB, which would be our two matrices, would be equal to CA times B, would also be equal to A times CB as well. So we have associative property here of scalar multiplication. So the definition of identity matrix, the n times n matrix that consists of ones on its main diagonal and zeros elsewhere, is called the identity matrix of dimension n times n, and is denoted by this kind of matrix here. So we have ones on this diagonal here, and then there's zeros everywhere else. This will be called your identity matrix. Note that an identity matrix must be a square. When the dimension is understood to be n times n, you can denote I to the n simply by I. So I would be the same thing as I to the n. So for example, if A is an n times n matrix, then the identity matrix has a property that A to the I to the n equals A, and I to the n times A would also equal A. For example, this situation here, we have A, and then our identity matrix here, ones here, zeros everywhere else, will equal back to A again by multiplying A times our identity. AI will equal A, and IA will equal A as well. So I times A will equal A as well. Excuse me. So applications, what do we do with that? So matrix multiplication can be used to represent a system of linear equations. Note how the system here, A11 x1 plus A12 x2 plus A13 x3 equals B1, B2, and B3 can be written as the matrix equation A times X will equal B. So that is something to keep in mind here. So what about that? Where A is a coefficient matrix of the system, B is the constant matrix of the system, and X is a column matrix. So here we are back here. A times X will equal B here. That would be the setup here that we get into. Okay, going on into our next example here. Solving a system of linear equations. Consider the following system of linear equations. Here is our system here. So A, write this system as a matrix equation, AX equals B. Okay, so let's write that down like that. In matrix form, AX equals B, the system can be written as follows. So here is our first matrix here. This is our A. This would be our X here, X1, X2, and X3. And then this would be our column here for our B. Okay, moving right along here. This is where we started out here, students. So B part of this example, use Gauss-Jordan elimination on the matrix A, therefore B, to solve for the matrix X. So to do that, the augmented matrix is here. Here is our A, therefore B matrix right here. This is our A, this is our B. Using Gauss-Jordan elimination, you can rewrite this equation as I, therefore X. So here is our I here. This would be our identity matrix here. And then when we do that manipulation, we start here, we end up here, and then we end up with -1, 2, and 1 over here. And this is where I want you students to know that this is where we started. That's where we got that from. Okay, getting that far into our example. So the solution of the system of linear equations is x1 equals -1, x2 equals 2, and then x3 equals 1. The solution of the matrix equation is x1, x2, x3, and that lines up over here, -1, 2, and 1 as a column. And then this would be how it would look here on your calculator. Here is your identity matrix here for that, and you end up with -1, 2, and 1 for that. Okay, let's try one. So in these exercises, A, write the system of equations, this is our A here, as a matrix equation, AX equals B, and then B, which is here, use Gauss-Jordan elimination on the augmented matrix, A, therefore B, to solve for the matrix X. Use a graphing calculator to check your solution. So this is what we start with here. So this would be our write the system of equations as a matrix equation. So here is our A, here is our X, and then here is our B here. So this we get to here from here. So that would be the A part of our example. And then B, by Gauss-Jordan elimination, we have 1, -2, and 3 equals 9, -1, 3, -1 equals 6, 2, -5, and 5 equals 17. So moving from there, for our B part, we do our manipulations, row manipulations until we get this reduced echelon form of a matrix with 1, -1, and 2. So we have as our solutions here, x1 equals 1, x2 equals -1, and then x3 will equal 2. And then here is our answer form for x, be 1, -1, and then 2. Into our next example here. Softball team expenses. 2 softball teams submit equipment lists to their sponsors as shown in our table here. Here's our equipment. We have a women's team and we have a men's team here. And then we have our number of items here for each team from this category here. So the equipment costs as follows: $90 per bat, $6 per ball, and then $60 per glove. Use matrices to find the total cost of equipment for each team. So to do that, the equipment list E can be written as a matrix. So here's our matrix here for equipment: 12, 15, 45, 38, and then 15, 17. So this can be written as a matrix. Once we have done that, here's our equipment matrix. You can find the total cost of the equipment for each team using the product CE, because the number of columns C is 3 columns equals the number of rows of E, which is 3 rows here for E. Here's our 3 rows here, and then C has 3 columns. Therefore, the total cost of equipment for each team is given by so therefore the total cost of the equipment for each team is given by CE equals 96 and 60 times our equipment matrix here. This is our cost matrix, and then this would be our equipment matrix here. So having that, we can go ahead and multiply out our matrix multiplication here. These are our products here for that, coming from this matrix multiplication here: 90 times 12, 6 times 45, 60 times 15, 90 times 15, 6 times 38, and then 60 times 17. And then we can go ahead and add that up, and we get 2250, 2598. So the cost of the equipment for the women's team is 2250, and then the total cost of the men's team would be 2598 there. This is the way it should look on your screenshot on your calculator once you do this multiplication on your calculator. Notice in example 12 that you cannot find the total cost using the product EC. So if we like flipped our order of our multiplication, we would have this, and that would not work because EC is not defined. Here's E, here's C. That is, the number of columns of E, 2 columns, does not equal the number of rows of C for 1 row here. Okay, so let's try one now. We got to here. How do we get there? So here is our A. A fruit grower raises 2 crops, apples and peaches. Each of these crops is shipped to 3 different outlets. The number of units of crop I that are shipped to outlet J is represented by A to the ij in this matrix here. So here is our matrix for this situation. The profit per unit is represented by the matrix B is $3.506. Find the product BA and state what each entry of the product represents. So here is our product set up here for BA is 3.50 and 6. So this would be B here. The profit per unit is represented by this. And then here are our, this matrix here represents our crop. Each of these crops is shipped to 3 different outlets. So this will be our 3 different outlets here. We have a 2 by 3 matrix here. So when we multiply that out, that's up to you, students, to multiply that out. And that is your 7.5 part 4. pre-calculus math today. My email is animaterpowerpointmathvideo@aol.com. Email me for solution PowerPoints, for classwork sheets, homework sheets, or any other course materials. Thank you very much.